This is the tutorial video about data acquisition and software operation process. This video includes details of the PIV data acquisition and how to operate the analysis software. Before starting, the setup explained in tutorial video 3 must be satisfied. First, set the time between pulse. This value represents the time interval between pulse laser emissions, which serves as the time step in velocity calculations. As the flow velocity increases, the time between pulse should be decreased. In this video, the conditions are 3 GPM, and Reynolds number is 500, so we will set it to 8000 microseconds. Now we will adjust the number of images setting. This refers to the total number of images captured during the data acquisition process. If you divide the number of images by the trigger rate, you get the total time required for data collection. Typically, data is collected for about 10 to 20 seconds. We'll set it to 100, which means the system will capture images for 20 seconds. As mentioned earlier, this duration is determined by its relationship with the trigger rate, which refers to the frequency at which the pulse laser is emitted. Now, let's see for ourselves how things change by adjusting the pulse laser. First, let's run it at 5 Hz.
So this is 5 Hz.
And now we will run it at 9 Hz. You will see the difference. The trigger rate is determined by the flow velocity. The faster the flow, the higher the trigger rate. Before starting, set the number of images to 1 for a moment and take a single photo for calibration. The other settings won't affect this step. Click the Acquire button. Once the system finishes running, click the Save for Calibration button to save the image. Now go back to 100 image. Then click the Acquire button. Now, the process begins. When the acquisition is done, click Save for Database. Once saving is complete, name this including the settings to avoid confusion with other data. Now, change the settings and repeat the experiment under different conditions. Do the same things, and repeat. After data collection, the first thing you need to do is calibration. Double-click the image, right-click and go to the Measure Scale Factor. Now, a pop-up window will appear. In this window, you need to match the length shown in the image to the actual physical length. We will calibrate using the channel height, but you can choose another factor that you know its actual physical length. For example, length between each pin fins in horizontal system. Set point A and point B to the top and bottom of the channel with mouse, respectively. And enter the actual physical height of the channel, 20 mm in this input field. Then click OK. Now, we will define the mask. Select the pre-process and define image, while selecting the calibration image. If you did not set it before, a green rectangle will appear. Use it to cover the areas you do not want to include in the analysis. Note that do not, it is easy to get confused because of the green color. You can create the green mask easily by clicking and holding the left mouse button while dragging. After you finished, click OK. This will create a region. Now, in pre-process, click Select Masking. Now, it will ask you to choose from several options. If you go with the default settings, the green region will be marked as not of interest. We will proceed with the default settings. Now that the calibration process is done, we will analyze the actual data. Choose the previously defined mask by pressing the space bar. Now we can automatically mask all 100 images. Right-click, choose Analyze, Image Masking, and click OK with the default settings. Then, the automatic masking process will begin. After finishing the masking, right-click again, choose Analysis, PIV Signal, Adopted PIV, and click OK. Now we can set the image pixel units. First, you need to select the region of the data to analyze. Click and hold the left mouse button, then drag to make your selection. Now set the grid size. We usually use 16 by 16. The smaller the value, the more precise the data, but it takes longer to process. Now the software will start analyzing. Just wait for it to finish. The velocity vector analysis is now complete. All that's left is the image post-processing. Click on the window. And now we can adjust the number of the arrows. Set it so that only 1 out of every 4 arrows is displayed. In the scalar map, select U to display the velocity vectors. Then, set the color range and enter the minimum and maximum velocity values, so the figure can be visualized using the color map. In this example, the pixel resolution is not ideal, so further experiments under optimized and different conditions are necessary. Select the rainbow in the scale map. Then choose Smooth, and it goes to look better. Since the colors are still too bright in the low velocity regions, lower the velocity range a bit more. What we've obtained now is a time-dependent image. By tracking particle displacement between double frames, we can calculate the velocity. With a trigger rate of 5 Hz we get 100 velocity field images spanning from 0 to 20 seconds. So we also need to obtain the time-averaged graph. Right-click, then go to Analysis, Vector and Relatives. Then choose Vector Statistics. And just click OK. After the coffee break, we can obtain the time-averaged vector field. Now, use the same visualization method for the graph. At this point, use the same velocity range as before. Now, what remains is to optimize the PIV parameters according to the experimental conditions, and the issue where the velocity near the inlet couldn't be observed due to the darkness of the screen, and the removal of noise caused by contaminants on the acrylic or the camera. This concludes the tutorial video on the PIV experiment. So far, we've covered degassing and channel assembly for experiment preparation, operation of the pump and laser system, data acquisition, and both pre-processing and post-processing of the experimental data. Now, only one thing remains for us: repetition.